Hello everyone, my name is Vivek Pandey. This is January 2026 and this is the second video of the series of video in which I am documenting my journey to create a very powerful, hopefully a world-class, world-beating chess engine. And if you have not seen the first video, the main motivation is for me to create this chess engine is to learn about various neural network architectures, about reinforcement learning, and then later on my overall aim is to apply these techniques to be able to solve math problems. We know that AI is being used to solve research level math problems, and deep reinforcement learning is an integral part of that. So I want to understand this area a little deeply, and chess provides a well studied lot of material is available on the internet about how to create a chess engine. So chess provides a good sandbox problem to understand all these concepts. Last time we implemented a value head and we saw the performance, it reached around ELO of 1400. This time we will implement policy head. So here is the summary of the talk. We will summarize what we did last time and what was the performance, and what we will do this time and what will be the performance, because I have done all the training and performance observations. So first we will summarize last time and this time, then we will go into the main part of the video. We will recap what we did last time, because we will be building up on the neural network that we implemented last time. So since last time we implemented value function and this time we are going to implement a policy function, first we will understand what is a policy function and how it helps us to navigate the game tree more thoroughly. Then we will see two intermediate steps. So when I implemented policy function, I did something, I realized that it can be much better. Then I did something else. Then again the network was doing some obvious mistakes. Then I again realized my mistake or other improvement areas. And then I took the solution steps. So I will be taking you through some of these intermediate steps. This is quite instructive. Then I will tell you the final solution which I implemented. We will actually implement it using Claude, and we will run it on a GPU. It will take around a day for the training to converge, and then whatever engine we create, we will look at how it performs against Stockfish, and we will see its ELO rating and all. It will reach around 2300, which is pretty good. And then we will see, then we will have some closing comments on what are the ideas for improving the engine further. There are a lot of areas of improvement remaining. Every few weeks I do some improvements in the engine, and then I create a video to checkpoint my progress, and then I do the next part, apart from doing other things that I do. Okay, so here is the summary of the last time. Last time we trained a value head. So we had a board representation. Then there is a neural net in the middle. We will see in the recap how it looks like. But finally, it outputs a number from -1 to +1. And so -1 means black is completely winning, +1 means white is completely winning. If it's 0, it's a drawn situation. So the neural network thinks higher it is, better it is for white, and lower it is, better it is for black. Then using this value head, we play chess against anybody who wants to play against our engine using a 3 deep search. We call it 3-ply search. So we do a 3-ply search to find the best move, and we found that we attained a ELO strength of around 1400. So 1400 ELO strength is decent. It's not bad, but if you practice chess for maybe, if you don't know chess and you practice it for maybe very hard, you work quite hard, in maybe 1 year you will be able to achieve a 1400. This time we will train policy head to complement value head. So what policy head will do is that it will output the most promising moves. So maybe there are 30-40 legal moves in a given position, and in the last time we don't know which of these 30-40 moves are good and which are bad. So we explore the game tree by going through all these 30-40 punches, and then from each of the 30-40 resulting positions there are further 30-40 branches and so on. So we are able to do only 3 ply search. Because beyond that it starts taking a lot of time, several minutes for the engine to calculate the move, so we stop at 3 ply search. But when we have policy, then the policy function will output k most promising moves. You can set whatever value of k you want. I mostly have set it to 6. So it will the policy will output 6 most promising moves, and we will not therefore explore the whole all 30-40 moves. We will only explore 6 most promising moves at each step, and therefore and so we can go wherever whichever part of the game tree we want to explore, we can explore much deeper. And so at the time of gameplay we will be playing using 7 ply search rather than 3 ply search, and we can afford to go deeper while maintaining the same move time, because we are not searching everything. And we will see that our engine attains a ELO strength of around 2300. 2300 is a serious strength. It is a candidate master level strength. So it's a really good. It's not yet a grand master, by the way, but it's candidate master, which is getting there. And a critical difference between the engine of the last time and this time is that the engine that I coded up last time, I was able to defeat that engine repeatedly. So probably my strength is a little more than 1400. I think it's should be 1700 maybe, but this time it's just I just cannot defeat it. I played many times. If I played 10 games, I lost all 10 games. There is no chance that I can defeat this engine. All right, so now let's go ahead and do the recap of what we did last time. Our network proper takes as input a 18 cross 8 cross 8 representation of the board. So first of all we have this board which we convert to 18 cross 8 cross 8 tensors. We covered last time how exactly we convert it to 18 cross 8 cross 8 binary numbers. And then the neural network consists of a convolutional layer followed by batch norm followed by value, which is followed by 8 ResNets. So this is one ResNet block. There are 8 such ResNet blocks. So convolutional layer followed by 8 ResNets, followed by another convolution, followed by fully connected layers, followed by fully connected and tanh function. Tanh outputs number between -1 and +1. -1 means black is completely winning, +1 means white is completely winning. So this is our neural network. We fed it 306, I forget how many positions we trained it on. It was, I think, 3.6 million positions, and we had a decent neural network. So there is this neural network, but then so given any position, this neural network outputs the eval of that position. How good does it think? What is the evaluation of neural network as to whether this position is advantageous for white or whether this position is advantageous for black? So the network doesn't tell what move you should make. That is a separate code altogether. The way we play chess is by something known as 3 ply search, and it is a good idea to understand this a little bit thoroughly. So let's say that we have been given a position some random position which has come in the game, and let's say that it is white to move, and let's say that white has 3 possible moves. In the real game, white will probably have 20, 30, 40 possible moves, but drawing that will become quite cumbersome. So we will assume that white only has 3 possible moves for the sake of illustration. And for each of those 3 moves by white, when we get the position, next position, then it will be black to move. Black also has 3 possible moves. Once again, actually the branching factor will be much more, and black will have different number of moves in different positions. So maybe this is like 40, the next branching is like 32 or whatever. But let us assume that for the case of for the sake of illustration, let us assume that in each resulting position black has 3 possible moves. Then again let us say that in each of the resulting position, when there is white to move, white has only 2 possible moves. I wanted to make it 3, but the diagram was becoming too noisy, so I said that okay, in the last level white only has 2 possible moves. This will help to illustrate the point. For the moment, don't ignore all the labels, all these evals written on various nodes. To begin with, there are no evals. We only construct this game tree. We only construct this 3 deep game tree. And then what we do is that for these leaf nodes, let's call them level 0 nodes or leaf nodes, we ask neural net to find the eval of these nodes. And let's say that neural net comes up with the 0.2 for this particular node, 0.3 for this particular node, and so on. Just a minute, I will be back. Okay, so I am back. So we were discussing that we ask the neural network to evaluate all the level 0 nodes, and let's say that it comes up with these evaluations. Then what we argue is that at this particular level 1 node, it was white to play, and white should take this right path because right path leads to a larger evaluation, and white would like larger evaluations. So white will take this right move. So we will say that eval of this particular node will be the max of 0.2 and 0.3, which is 0.3. Note that we will not ask neural network for the eval of this position, because the farther neural network is not perfect, we know. So that eval function is not perfect. Real thing is the real gameplay. So if you do the tree exploration and ask the neural net to find the eval of these leaf nodes, then that is much more deeper in the game, and therefore it is likely to be more accurate. So this way we find out the evals of all these level 1 nodes. Then we go further up. We say that okay, when at this position it is black to move, and black has 3 possible choices, one leads to an eval of 0.3, another 0.2, another 0.3. What should black move? So black should take that path which leads to minimum eval, because that is the objective of black. So black will choose this middle move, and so eval of this particular position, this particular level 2 position, will be the min of all these 3 children. So it will be 0.2 here, min of minus 0.2 plus 0.1 plus 0.2 is minus 0.2, which is here, and so on. So note that there was a position at which leads to plus 1, which is completely winning for white, but black avoids it. Black doesn't go there, even if white were to land here. Similarly, there was a completely winning position for black, which is minus 1, but white avoids it. Why will white go in that particular direction? Okay, so we go this way, we evaluate level 2 position evals, and similarly level 3 eval, and then we Well, level 3 eval we don't need to evaluate. Nobody is asking for it. We only need to find out the move that we should recommend for white. We should play as white. So, and clearly that move will be, so at the top level it is white to play, and white has three possibilities. Two of them leads to positions with evals minus 0.2. So white will choose the one which has the max eval, which is 0.2. And so this is how the game tree will be constructed and game will be played. So ideally I would like to do deeper and deeper evals, but we are constrained by the time and memory, so we choose we just do the we just take some depth which works out for us. So when in the last time we did 3-ply search, we saw that 3-ply search takes like 20 to 40 seconds per move, at which at that rate I can play some games in like 30-40 minutes one game finishes. Beyond that it becomes 2 minutes per move, and more than 2 minutes per move, and I don't have that much time, so I took only 3-ply search. And this is the this I did not present in the last video, because I did these things more deeply only after I had already finished the last video. So Stockfish engine, you can play it at several skill levels from like 0 to 19. Actually you can go a little higher also, I think 20, 21 or 22. Okay, and this is the graph that I have gotten from this website. Let me take you through this official Stockfish website. Yeah, so this is the graph. They have provided us with when we set Stockfish level at a certain value, then what is the equivalent ELO of that? And how does Stockfish implement those skill levels? It is provided in the document. You can read that if you want to, but for this video we can only say that higher the level of the Stockfish, better the gameplay is, and you see better the ELO rating is. Let me try to wait. I want to get, yeah, this is the we are back. Sorry. Yeah. Okay, so I would finally like to beat like Stockfish level 18, 19, etc. But right now, I mean, in the last video, what I told also in the last video is that if this engine, the last engine, the value head engine, if it plays Stockfish level 0, it wins more than it loses. Stockfish level 1 is something like an equal performance. Stockfish level 2, again we are able to defeat. So maybe our performance is somewhere between like something like maybe 2. It is an anomaly that we are able to defeat Stockfish level 2 but not 1, because hey, there is some randomness also associated. But Stockfish level 3, 4, 5 are totally out of reach of this particular engine. So let's say somewhere between 2 and 3 was the rating of our Stockfish of our engine. So it was level 2 is like sorry, somewhere between 1 and 2 was our rating. Level 1 is like 1440, and then level 2 is like 1500. And last time I said that okay, my engine's ELO is something like 1400. So this is what we did last time. So now that we have done the recap of last time, let's get to what we are going to do this time. And since we are going to implement the policy function, let us first understand the idea of policy. So in our first part, when we implemented only the value function and we did that 3-ply search, we could do only 3-ply search because time and space requirements increase exponentially with depth. So if we are able to do like 50-60 ply search, then probably would have solved the game of chess completely, but we are limited by time and space. and at each position there are anywhere between 20 to 40. Well, sometimes chess moves have only one possible move, but often usually there are 20 to 40 possible moves. Now, the idea of policy is that if we can figure out the 5 or 6 or 7 or 8 or something like that, most promising moves, then we can only explore the positions which are resulting after those moves. And that way we will have time to search deeper. So the idea is that if there is a silly move, then I mean, which is obviously silly, if we can figure that out, then we won't explore that move at all, and we will only explore 5 6 most promising moves, and then we will pick one of those 5 6 most promising moves. And that is the idea of policy head. So the job of the policy head will be, give me 5 most promising moves. Given any position, output 5 most promising move for white or black, whosever move it is, and that part of the game tree I will explore. So the question is, how will we train policy head? Let me change my video because it is coming in the middle, or let it be like, yeah, let me actually change it. Wait a minute, can I change it while here? Yeah, I can move it while I am having this video. Great. Okay, so the way, so this is another representation of our current neural network. There is board, and then there is convolutional layer, then there is a bunch of ResNets, and followed by some more layers. And so this path is what we have currently, and let's call this first convolution and the bunch of ResNets as the backbone. So we have a backbone, and we have what we call value head, a specialized network to find out the value. So this backbone creates essential features, analyzes the position, etc., and then value head operates on the computed features to compute the value. So the idea is that, can we have another head known as policy head, which will output for any given position the top moves? So maybe for a certain position, d4, it says that d4 is likely to be the best move with probability 32%, and king to e2 will likely to be the best move with probability 22%. Actually, these moves are not valid moves in this representation, in this particular board that I have given, so please pardon me for that. So it will, the policy head will give me all the legal moves sorted in the along with the probability with which they are likely to be the best moves, and then I will pick top 5, top 6, top 7, whatever my time budget and whatever my compute budget allows, and then I will explore the game tree in that path, in the resulting with those moves. So that is the idea of policy head. So I did several 2-3 attempts to code a policy head, and then something worked quite well. So the first idea that I had was that, hey, a move consists of a source square and a destination square. So when we play a move, we pick a piece from a square and place it in a certain square. So I thought, how about I code up so this is the backbone till ResNet 8 is the backbone. So the backbone remains as it is, and then there is a value head which is being computed that continues to be there, and then I have 2 more heads. Let's call it a source head and a destination head. So another bunch of convolutional fully connected softmax layers, and it will give me the probability that each of those, what is the probability for each of the 64 squares that the optimal move starts from that square. So the piece which is to be moved is currently sitting on that square. And similarly, there is a destination policy, the policy for the destination. So I thought that I will have to calculate these 64 plus 64 equal to 128 numbers, and this is how I will implement my policy function. And I actually implemented it and ran it, and then I then I was led to some problems, and there are these two problems that I realized only after implementing. But the good thing is that with the Claude and all tools, the implementation cycle is quite fast, is quite quick. So even if you do some mistakes, you can learn from the mistake very quickly and go on to the next thing. So there are two problems with these ideas, with this particular idea. The first is that, okay, you have found out probability distribution for the source square and for the destination square, but how do you figure out the optimal move? So let's say that e2 to e4, the pawn move, was the best move, and therefore therefore network will give high score to source e2 and also high score to destination e4. But if e2 as a source has been given high score, then even e2 to e3 move gets advantaged because of this. But e2 to e3 may be a bad move, so this doesn't work. So the main thing is that I actually there are 64 into 64 moves, but I am trying to, so I should be finding the distribution of all the probability for all the 64 into 64 distinct moves. But what I am trying to do is to just find 128 numbers. So I cannot compress it from 64 into 64 to 128. All the moves are independent. So that is the first problem. And the second problem is that in this source to destination type of framing, we are not handling under promotions. So let's say a pawn moves from e7 to e8. So that's a move in my setting. But do you promote it to queen? Do you promote it to bishop or to rook or to knight? What do you promote it to? So that is something that I have not considered. So I thought that this is a good idea, but then I gave up this idea and moved on to the next thing. And the next thing was, and actually I got this next idea from Claude only. Claude has read through AlphaZero. No, probably AlphaZero is maybe not open. Yeah, I think it is open source. So Claude has read through AlphaZero code and through Leela Chess Zero code and so many other chess programs. Claude already knows about them, so it can if you ask it rightly, it tells you what great people have been doing in any given area. So I asked Claude, what do you think? And then it told me a 64 cross 73 representation of the possible moves. So we encode the move not as source and destination as what I was trying to do earlier, but as source square move type tuple. So let's see what it looks like. Any move will move a piece, and that piece will be on one of the 64 squares. So the source square can contain 64 possibilities. Okay, and then there are 73 move types. So once you have chosen that this is the piece that I want to move, in what ways can you move it? And we are not figuring out only the legal moves in the current context, but overall what is a superset of the moves that you can make. So this is one way to do it. You can pick a direction in which you want to move that piece, and so these are, in the first bullet point we are considering queen like moves. So you can go in any of the 8 directions, the 4 horizontal and vertical directions and the 4 diagonal directions, and maximum 7 distance you can go. So that is the that gives us 8 into 7, 56 types of moves. So it's not that your piece can always move that. It's not that in a given position all these 56 moves are available, but overall your move will be one of those 56 moves. Similarly, there are 8 knight moves. Knight can move at most in 8 directions, so in 8 ways. So there is this 8, and then there are 9 under promotion moves. Okay, in these 56 moves, we assume that if a pawn reaches the final rank, then it is promoted as queen. Okay, this is the assumption. But then we have to consider the under promotion moves, and there are 9 under promotion moves which are possible. The pawn can move in 3 ways: up or left up or right up. And it can be, and there are 3 possible under promotions: to knight, to rook, or to bishop. So there are 9 under promotions. So we say that there are 73, 56 plus 8 plus 9 is 73. There are 73 types of moves. So any move we can encode as 64 cross 73 bitmap. So what we will be outputting therefore is actually 68 cross 8 cross 73 I think not 8 cross 8 cross 73, but a 64 cross 73 tensor is what we will be outputting as a result of our training. So note that this is a wasteful representation. For example, a pawn on a1 cannot go south or west, but we are saying that but we keep it nonetheless, because this is geometrically quite simpler, much simpler, and it is therefore easier for convolutional networks to understand. So once again, so we have a 64 cross 73 cross 73 possibilities. So a given move will have one of these bits set to 1 and all other bits set to 0. So that will be the representation of a given move. As I told that AlphaZero uses this, so we are in a good company. We are on a well-trodden path. So now, actually, I will take a break now and then be back in some time. Okay, I am back. So our plan for training is that we will take the 3.6 million training positions and 360,000 test positions that we have already created last time. So last time what we did was that we took some n games, lots and lots of games, and resulted and calculated all the positions that resulted from those n games. We found the evals of all those positions and then took a subset of those positions, 3.6 million plus 0.36 million, such that the eval was roughly equally distributed. Because normally most of the evals are very close to 0 because nobody is really winning, the position is close to equal, but we did not want to have our the data distribution such that most of the evals lie in the middle. So we took a such a distribution that extreme evals were as frequently happening in our training positions as the median center evals. Okay, so we will take these test and train positions from the last time, and then for all these positions, what we will do is this. We will take we will take a given position P, we find its eval E0, we already know that eval E0 from our work last time. Then we find all the legal moves M1, M2 up till Mk for each of these yeah, so we find the legal moves for this position P, and then we find the eval after each of these moves. Note that these evals would be found by the stockfish because they are the ground truths for us. This is not to be computed by our engine or from the previous version of our engine. No, this is the ground truth. So we will be using stockfish, our guru, for these evals, and then we will find d for, let's say, delta equal to ei minus e0. So for each move we will find out how does it impact the eval. Does it take the eval up or does it take the eval down? And then for a moment let's assume that it is white to play. We will find those moves which impact the eval most positively, as in which change the eval the most in the favor of white, because let's say it is white to move. For black to move, we will pick those moves which take the eval most down, and if it is white to move, we will take those 5 moves which take the eval most up. So let's say that position that moves MA, MB, MC, MD, ME, one of those five moves out of those K moves, are such that they make the eval most in favor of white. So EA minus E0 is largest amongst all EI minus E0. EB minus E0 is second largest, and so on. And so this is assuming it is white to move. If it is black to move, then we will take the lowest values of these DIs. Okay, so we will say that these 5 moves are the top 5 moves. Fair enough, right? So these 5 moves we will say are the top 5 moves, and this MA and EA, actually I have done a mistake. Actually in training we don't store MA and EA, but we store MA and DA. Yeah, actually I have written this. DA, DB, DC, DD, DE are the deltas for the top moves. So we will store MA, DA, MB, DB, etc. in some file. This is our training. This is the creation of our training data set. So we have already stored evals from the last time, and now for each position we also store top 5 moves and the deltas that they cause in the initial position. And what we will do at the training time is that we will say that probability that move A is the best move will be E power dA divided by E power dA plus E power dB, and so on. So you can say that you can see that prob A plus prob B plus up till prob E, the summation of probabilities of all 5 moves will be 1, and the top move will have the highest probability. So this is a standard softmax like technique, if you are aware of softmax. So this is how we will find out the ground truths for our training. Okay, great. So yeah, and we will so now we will be training 2 heads simultaneously. There will be a backbone of our neural network, then there will be a eval head or value head, and then there will be a policy head, and we will train both of these simultaneously. For eval head, we will continue to use Huber loss with beta equal to 0.2. This is what we did last time. And for the policy, we will use cross entropy loss. Let's delve just slightly deeper into what is cross entropy loss. So we have n equal to 4, 6, 7 2 possible moves. Many of these moves are illegal or whatever, but we have 4, 6, 7 2 possible moves that the network can output. And for a given position, let's say that T1, T2, Tn is the actual probability of those moves. So as in, let T1 be the probability that move 1 is the optimal move, T2 be the probability that move 2 is the optimal move, and so on. And this is the ground truth. This is what we have got from the last time, from the last slide. And if you, and we set, we only said that there are 5 good moves and the rest of the moves are bad. This is a reasonable thing, top 5 moves. Maybe there were 10 good moves, but never mind, we will just take 5 of them. So actually only 5 of these TIs will be non-zero, other TIs will be 0. Okay, so this is the ground truth gotten from Stockfish. And then let's say that our model says that a probability that move 1 is the best move is P1, probability that move 2 is the best move is P2, and so on up till Pn. Then the cross entropy loss is negative summation Ti log of Pi, and you sum it from I equal to 1 to n over all the moves. If so, why is this fantastic expression a good expression for the loss? We are not going to go too much detail into it. You can Google it, Claude it, etc., and find out why cross entropy is a good idea. In general, however, we can say that we can make this remark that if there are it is a way to measure the distance between two probability distributions. All right. So so this will be the loss for the policy head, and the total loss will be the summation of these two losses, value loss and policy loss. And actually we can weigh it. We can de-emphasize some loss and emphasize some other loss, and so on. When I practically did it, as we will see later, I found that numerically policy loss was more than 10x of value loss. So I was thinking that if we just naively add the two losses, then policy loss will get more weightage, because value loss is like, let's say, 0.2 in that range, and policy loss is like 3. Then the model will try to reduce this 3 rather than value loss, which is naturally smaller. So what I did was that I set the total loss as value loss plus 0.1 into policy loss. So this is what we will do. And at the inference, so this is now our model will, now our network will learn to provide, learn to output an eval as well as these PIs for each move. What is the probability that it is the optimal move? And what we will do at the inference time, that we will take the eval. We will need the eval because we will maybe go till depth 7 or 8, and in the end we will need the eval. But what paths to go up? I mean, we will not explore the whole tree till depth 7 or 8, because that is too compute intensive. So which paths we want to explore, that we will get from the policy head. And at the inference time, network will give that, okay, move 1 is good with probability 0.02, let's say, or something like that. What we will do is that we will take some 10-15 top outputs, top probability moves from the network. Some of them can be illegal moves also. Note that there is nothing stopping network from giving a high weightage to some illegal moves. If the learning is not good, that will invariably happen. There is no logic which stops that from happening. So we will invariably some moves will be illegals. We will prune those moves, and maybe so out of 10, let's say that we will take the 15 best outputs from the model. We will prune, and let's say that the list goes down to 10, and then we will take maybe top 6 or top 7, whatever is our fan out comfort level. And this is how we will play. So this is our overall idea developing so far. And now I actually coded up all these things that I told you, and then I encountered some problems. So and I want to take you through 2 problems that I encountered, one after the other. In the final coding that we do, we will only do the final approach, which is verified to be correct, but I am taking you through the journey. So what I found out was that sometimes I trained it, but and I trained it, and the engine was playing reasonably well, quite stronger than the previous version. But sometimes the engine was not able to spot a mate in one or mate in two move. Note that this problem was not there in the previous version, because in the previous version we explore all the legal moves. So if there is a mate in one move, I will catch it. But here I only ask the engine to give me network to give me top 10 or 15 valid move, top 10 or 15 moves, and some of them will be invalid. And the engine was not giving the best move, the mate in one move, and so my gameplay, the network was not giving the best move, the mate in one move amongst its top choices, and therefore my engine was missing mate in one, and this was surprising. I mean, we regressed from the previous one. We can explore till great depth, but we are missing mate in one. And then I figured out that there were very few puzzles in the training data. So as I described to you earlier, the way I constructed training data was by taking real positions from the games, and in real positions, mate in 1, mate in 2, in real games, mate in 1, mate in 2 happens very infrequently. So my model did not get trained on such positions. So that was the reason I figured out, from with the help of doing some web searches and Claude brainstorming, etc. So what I did was that I said that, okay, fine, I have 3.6 million and 360,000 train and test position. I will now add to it some more positions. So I took additional 400,000 training and 40,000 test positions from Lichess puzzle database. So Lichess has a game database and also a puzzle database. So it has some, I don't know, some tens of millions of puzzles perhaps. And the puzzles are meant, they provide us, they provide it to us to download, but you can go and manually solve some puzzles. While we are at it, why not let's solve some puzzles. That will provide you with some idea. Puzzles, yeah, puzzles. Let's see. Maybe is there some categorization of puzzles? Yeah, puzzle. Wait. Puzzle themes, and maybe by opening motifs. So there are lots and lots of types of puzzles. So there is a mate in 2 puzzle. Let's see if I am able to do a mate in 2 puzzle right here. This is whom to move, this is white to move, and it's mate in 2. Yeah, it's mate in 2. If you play chess, it's easy to spot. I will give a check, it kills, and then I take, and this is a mate. All right, and this puzzle's ID is a 3GFDE. So you can download all the puzzle, they provide you Lichess puzzle database, and yeah, so they provide you with you can download their file, and they have some okay, it has some 5 million puzzles. Okay, I'll go back to the presentation now. Yeah, so I downloaded this puzzle database, incorporated some puzzles, and puzzles are such that there is one clearly winning move and none of the other move is as good as this move. So for these puzzles, while constructing the training data, I said, okay, there is only one correct move with which provide a huge bump in the valuation eval of the position, and all the other moves are like they don't change the eval. So there is only one correct move, and that move's probability is 100%. Okay, so I did that. Okay, we will come to observation 2 later. So I did that, and then this problem was solved. Then the engine was by incorporating some puzzle, I think we call it curriculum training. That's the phrase I figured out while doing my research. So by doing a little bit of curriculum training, the engine was then not missing mate in 1 or mate in 2. Great. And then as I was observing some of the characteristics of this engine, I found another very curious and a little disheartening thing, and that is this. Look at this position. This actually the engine encountered in one of the games that it was playing against some stockfish level. Uh, uh, Black is under check, and black has only two legal moves. One is to capture back the queen, and the other is to run to square d6. There is no other legal move. Okay, sorry. There is actually a third legal move also. No? It can go to. There are two more legal moves. I'm sorry. There is not only. It can also go to c7. It can also go to c6. Okay, so it has four legal moves, and the best move is clearly to capture back the queen. Okay, so now what happened was that the network's top 15 moves did not contain kxc8. The top 15 moves contained one of these other valid moves, only one of these other valid moves. Actually, it contained kd6. That is how I have written kd6. And then it contains all sorts of illegal moves. Move this pawn, but you cannot move the pawn. Your king is under check. Move the knight, move the rook, all sorts of positions, all sorts of moves were there, but they were all illegal moves. Maybe they were actually legal if the king were not under check, but as of now, since the king is in check, they are all illegal moves. And this was like, how will the engine play if you don't even properly encounter, if you don't, if the network has not yet learned to give high probability to valid moves, then there is no hope. And then I learned that the problem is that the network has to work with 4, 6, 7, 2 outputs. Network doesn't know which moves are legal and which moves are illegal, and it is difficult for network. It needs to reduce the probability. So generally, not only in this position but in general, the network not only, it needs to do two things. One is that it needs to figure out that amongst all the valid moves, which are the best valid moves, and it needs to also figure out which moves are valid, which moves are invalid. It needs to lower the probabilities of all the invalid moves. That is quite a bit of task. Maybe if the network capacity were huge, then it will be able to do that, but my model is like 10-12 million parameter model. And while debugging that, I figured out the concept that there is a concept of legal move masking. We'll pause the video here and learn about legal move masking very soon. All right, I am back. So let's understand the concept of legal move masking. So I told you earlier that we use this cross entropy loss as the loss for the value head. And to revise, cross entropy loss is this expression where T1 to Tn are the target probabilities, the correct probabilities for the moves, which has been derived from stockfish, which we are using as the ground truth, and P1, P2, Pn are the predicted probabilities. Then this is the loss. And how is pi calculated? Pi is calculated like e to the zi divided by summation of e to the zj. So this zis are the logits. They are the outputs of the layer just before the softmax. So just before the softmax, we have a layer which outputs these zis. To zis, we apply softmax and we get pis, and from pis we compute this loss. Now the concept of legal move masking is that when we are calculating the probabilities of various moves, we will consider only the legal moves. We will not consider illegal moves. Therefore, illegal moves therefore will get a probability of 0. We This is by fiat, this is by mandate. Network doesn't need to learn it. In particular, so what will happen is really that the network will output some for any position. Network will output some ZIs, some logits, some ZIs, and even for invalid moves, it will output some logits, whatever is its understanding. But at the time of computing PIs, we will consider those logits to be minus infinity. If you consider some logit as minus infinity, then the corresponding probability will come out to be 0. And therefore, what will happen at the time of backpropagation is that only the network's logits or network probabilities for the valid moves will be considered. Only your logits for the valid moves will impact your backpropagation, and therefore it will impact only that will impact how the weights are adjusted for the next round. So this is the legal concept of legal move masking. And so the idea is that what you do for 1 minute. So the idea is that what you output for non-legal moves doesn't even matter. So you don't need to learn that. So once I did this, okay, one more thing to consider is that once we do this, then the model is actually as a part of model output itself, we are mandating that we will output legal moves only. So the kind of problems we encountered earlier, we have what was that problem? Yeah, the kind of problem we encountered earlier, that network was outputting all the junk moves, like move this pawn forward or move this rook somewhere else. Such moves cannot be outputted. So that is one thing. And another thing is that model's capacity is better utilized because it doesn't need to distinguish between legal moves and illegal moves. So now let's go to the let's go to the coding part. And so this is all, as in I have described all my experiments, etc. And now we are ready. So, and we have a final approach. Now we are ready to apply that approach and actually get something. So what we will do is, we will first prepare the data. We will start from the previous data set, which we have calculated in the first video. We will add to it some puzzles. So then we will have an augmented data set. So we will have an enlarged data set. We will augment that data set with the top 5 moves and their scores. So this will be our data. Then we will write the code for the new training. It will jointly train eval and policy. And we will give the weight of 0.1 to the policy loss, as I described earlier, because practically I noticed that numerically policy loss is much bigger than eval loss. So if we weigh each of them equally, then model will spend its more of its capacity in policy. But I wanted policy and eval to be treated at par. I don't know what is the best thing. I want to treat them as par because I don't have any better ideas. And then we will run that. So yeah, so let's get to doing that. All right. So while I have done all this earlier, let's see if I can do it again live. So this directory attempt 01 is the directory from the last time. And last time we had created this chess engine.py, which had as 18 plane representation as its input, and finally 10h output, 10h final 10h, yeah, so something between -1 and +1 as the output. So this was the last time. We will start from this and implement the policy also. And and our first order of the day is to start with the data preparation. So let's create a directory called attempt02. This is our round 2, and we will first download the data that we have currently. So we have a training data.csv and we have a test data.csv. We will download both these files. Training data.csv. It will take how long? Like 16-17 seconds. Fine. This is the file that we created last time. Actually, yeah, you can see the timestamp also, December 31. This was just a few days before I did the first video. And then there is the test data.csv. We will download this file as well. So now I will get these files from where they have been downloaded. Let's see how they look like. Yeah, so they look like the position and its eval. So this is some position, and then this is its eval. And this is another position, and its eval is very, very huge, 59.76. So this must be completely winning for white. Why don't we just see this position and see that it is actually completely winning for white? We'll go to Lichess and Tools Analysis Board, and here I can input any fen. So I copied that thing here. Yeah, so you can see this is 3 pawn versus here it is 1 pawn. Clearly white will be able to promote one of its pawn to the queen and win the game. So this is indeed really yeah, so just a quick check shows that these evals should be correct. And similar is the case with test data.csv. That is also of the same format. In training data, we have 3.6 million examples. I'll increase the font a little maybe. Yeah, in training data, we have 3.6 million example. The first row is for the header. And in test data, we have 360,000 examples. Now, I said to you that we will get the puzzle database and augment this data. But let me actually change the plan a little for some practical reasons. We will first augment this data, and then we will get the puzzle database thing. Okay, so we will get to Claude. I use tmux as my terminal multiplexer. We have 2 things here. Yes. Now we will get to Claude and we will say to it, wait a minute. Look at training training data.csv and test data.csv. These files contain positions for training a chess engine. The first field is fen string and second field is eval. I want to augment this file with top 5 moves and their scores, the delta of eval from the base position got from Stockfish level 16. So level 16 is a very Stockfish has several levels. We play with level 0, 1, 2, 3, 4. By the end of this video we will be equaling in performance with level 6. But so level 16 is a very high level engine for us. It is good enough to be our guru. Our dream is that sometimes we should get beyond the stockfish completely, and then we will need to rely on reinforcement learning, self-play and all to go beyond that level. But so far, as long as we are weak, we can take lessons from the stronger engine. So I want to augment this file with top 5 moves and their scores as got from Stockfish. The format of the output will be fen eval move 1 score 1, move 2 score 2, move 3 score 3, move 4 1 2, move 4 score 4, move 5 score 5. Let's see what happens. Yeah, Stockfish is hopefully available. The Stockfish should be available. Do you want to proceed? Yeah, Python chess should also be available. All right. Wait, it is saying that it is not available. Okay, wait. No, use virtual env tilde slash myvenv slash bin slash activate. That has Stockfish. That has all needed dependencies. Good. Dependencies are available. This will need multi-processing. Yeah, okay, fine. What is it doing? hw.ncpu. I don't know what it is doing. Has it created any files yet? No. It will ask me before it creates any files. Let's see. It's taking fair amount of time. Fine. Okay, finally it has augment with top moves. It is writing that file. Let us has it written the file? Yeah, let's see the file by the time it checks. Okay, yeah, fine. So yeah, maybe yeah, parser some arguments are being taken. Fine, then task queue process. Yeah, so probably this is the main thing. Target equal to worker process. I am looking for where it calls Stockfish, perhaps in analyze position. Yeah. So it is it is getting the board from the fen string, and then it is asking Stockfish to analyze. This engine, I'm sure, has to be the Stockfish engine. Analyze position, and yeah, analyze position is taking Indian as is being given Indian as an argument, and the Indian is this stockfish. Yeah, so we are opening stockfish engine. Stockfish follows some particular protocol. So protocols perhaps called simple engine protocol or something. So we are asking here results. We are asking here stockfish to analyze the position, give us the results. What is a multi-PV? Multi-PV equal to multi-PV. Yeah, so we are asking stockfish to give us either the num moves or whatever is the number of moves available, minimum number of moves available. So here we are asking stockfish to give us 5 results. All right, yeah. So we have this thing ready, and I am not sure what this guy is doing. Let me pause the video, and once this finishes, I will start recording again. Okay, I am back. So in the intermediate time, Claude found some error in its own work. And do I have that thing? Yeah, no, not really. Yeah, it found some error. Yeah, I see the test here and hit a bug. It found some error in its code, then it corrected it. Now it's claiming that it's all good. So it was proposing that it would like to run it on these files, and it would take a long time. So I said ki I will run it myself. So I will run it myself. But before that, let's check whether it is correct or not. How to, yeah, it is actually showing us how to run. We have to give the training data input file and the output file as example. So let's do one thing. We will create a simple position just to test. So let me create a simple position. Hold on. We will I want to create a simple position whose answer I know, so that then I can test this program that it is indeed working, it is indeed giving correct result in those simple positions. This is the starting position. Let me place some moves. Wait, I don't want to play this. I want to set up a scholar's mate. Yeah. And now this one, and now this is a scholar's mate. So this is the position which I want to give. Okay, so what I will do is let me call it a.csv and fen eval, and this is the fen, and the eval is anything. Eval is like 20 because white is completely winning in this situation. Is that the format of the test data? Yes, fen and eval. Okay, now I will run this program. Let me start my virtual environment /my1/bin/activate and 3, no, not test data, but what to do, a.csv and a augmented.csv. Let's see, a Python 3, and the program is augmented, etc. All right, let's see what happens. It's launching some 8 processor and all, but anyway, it is done. And let's see if a augmented has come up. Yes, a augmented has come up, and it is saying that f3 f7 is the best move, and indeed yeah, this was our position. Indeed, f3 to f7, this is the square f3, this is the square f7. F3 to f7 is the best move, and it moves the eval up by 80. Is it pawns or is it centipawns? It has to be centipawns. So it moves the eval up by 80 centipawns. All other moves lead to actually decrease in eval. Otherwise, white has not played good moves so far. They pulled reasonable moves only, but anyway, we know that this is the winning move, and it is being indeed outputted as the top move. So this is doing well. So what now I will do is I will run this uh, program on the real file. So I will run it on train and training data augmented dot csv. This will take a bit of time, so I will be back. So I will let it run, then I will have it run on the test data, and when both files have created, then I will be back and we will continue from there. Okay, so I am back. The program finished. I ran that. I ran it once with training data, once with testing data, and now we have two files: training data augmented.csv and test data augmented.csv. Training data augmented.csv continues to have 3.6 million lines, and test data augmented.csv continues to have 360,000 positions. And let's have a quick look at one of these files, or maybe both of these files. Yeah, so now we have not only the fen and the eval, but also the moves and the scores of the moves, which are the deltas of the moves. Let's quickly see if it is indeed calculating delta. Is it doing some minus somewhere or not? Analyze positions. Yes, you see here it is finding the next moves evals. It is finding top 5 moves, and then taking the taking the move eval minus the base eval. So it is indeed doing that minus. Right. So now we have augmented the training data. The next thing, as per our plan, that we want to do is we want to put some mate in one positions. We want to just put some puzzle positions. So that it policy function can learn better about puzzles, which do comes these positions do come sometime. And if we don't include that, then we saw that it was a missing mate in 1, mate in 2 type of positions. So we'll go back to leeches. We'll find leeches puzzle database. So we have this leeches puzzle database. This is the puzzle database. We will download this file. Okay, I have already downloaded it. That is why this one is coming up. So why don't I use the already downloaded version rather than waiting for like 7 minutes for it to be downloaded again. So let me cancel this download. Let's see if there is already a version available. If that, then I will cp it. What was the thing? What was the file name? leeches _ db _ puzzles. Yeah, so I already have it. I will uncompress this file. What is it? zst d dash I don't know, decompress leeches, maybe this one. Yeah, it is this indeed, decompressing. Yeah, so now let us see. Yeah, there is a .zst file which is compressed, and then there is a leeches db puzzle.csv which is uncompressed. Let's look at some puzzle. Let me increase this window. Yeah, so there are lots of things about the puzzle. There was a puzzle id, and then there was a fun of the puzzle. And the following is something that I determined after some unsuccessful attempts, that this fen is not the fen of the puzzle. The fen of the puzzle will be got after this first move has been played. So let me that is where the puzzle starts. So let's see, for instance, well, this is a hanging piece, crushing hanging piece puzzle. So let us go to leeches again. I will set up this position. The problem with puzzles is also that maybe, I mean, seeing it manually is sometimes also that it may be too complicated for me to solve, and I will not even understand. Okay, but let's see, let's try. After f2 g3, the real puzzle will start. So f2, it is showing from the black side. Maybe it is black to move. It is black to move, so it is showing from the black side. Hey, can you please flip the board? I want you to flip the board. Can you do that, please? Uh, can we flip the board? Okay, I don't know how to flip the board. Wait, where? Okay, never mind. So the puzzle will start after f2 g3. So which is, this is f2 goes to g3. Okay. And okay, so see that earlier it was advantage for black, but now black has played a very bad move. And so this is the, Stockfish is already telling us that this is the right move. So anyway, what I wanted to illustrate was that after we make the first move, then the puzzle starts, and the right move is e6 e7. The right move, which is, I mean, the solution of the puzzle is e6 e7. That is why in this analysis Stockfish is immediately telling us that. So that is one thing. Another interesting thing is this, that the puzzles are such that there is only one solution. All player moves of the solution are the only moves. So this is interesting. This is very comfortable for us, that if they are giving, when they are giving the solution, that solution is the only move, and any other move is a worse move compared to the move that they have suggested. Okay, I am back on the next day. Today is 2nd of February, and I will now restart. So last time we had just yesterday we had discussed that we have the puzzle database, and we want to get incorporate some puzzles in our training. So I will restart Claude again here. Wait, let me do the, let me, since I'm restarting Claude, I will already go in my virtual environment so that it doesn't have to import it all the time. This is fresh, so I need to tell it again, since Claude doesn't maintain the context. So I will tell it that leeches, like this, yeah, contains some puzzles, specifically head minus, I want to get the format of the CSV file. Okay, specifically fen specifically okay, wait, leeches contain some puzzles. I want to derive training data from these puzzles. Specifically, I want to generate two files, training puzzles dot csv and test puzzles dot csv, containing 400k and 40k positions respectively. I will later on add these positions to, I will provide it training data.csv, training data training data augmented .csv and test data augmented .csv respectively. So read these files, read these augmented files to get the format of the file that you need to create. Okay, so I want to generate these two files. The way to generate training puzzles.csv and test puzzles.csv is to pick a random 400k 40k positions from this lichessdb puzzles.csv file, create the position by playing first move from move what is this called, moves, from moves section on the position provided in the fen section. The solution to the puzzle is the second move in the moves section. Get the eval of the position from Stockfish. Have only assign the score of plus 1000 or minus 1000 to the solution move. We will have only one move in the output, i.e. other moves are assumed to have score 0. Alright, so eval we will get from Stockfish, and policy we are getting from the solution of the puzzle itself, and only one move, whatever is the solution, that move we are saying has all the score, probability 1, everybody else is probability 0. That may not be the reality. I mean that is the reality in some sense. There is one unique best move. Maybe Stockfish wouldn't agree with that, but that's okay. We just want to do it in this format. Let's see. Ask any clarifying questions if things are not clear. Let's see. It's a pretty lengthy instruction to Stockfish, to Claude. So we already have augmented the base data that we used last time. Now we are getting some incremental data so that some curriculum training happens on the for the model, because otherwise it will miss simple mate in 1, mate in 2. Okay, for this, should it be plus 1000 when white is to move and minus 1000 when black is to move, consistent with the white perspective? Yes, correct. Enter plus 1000. This is consistent with the white perspective. Do I have a Stockfish? USR local bin Stockfish. I think that is the... Usually it doesn't ask. Since I specifically asked it to ask questions, it is asking question. Otherwise it usually doesn't ask. Okay, which stockfish opt homebrew bin stockfish? Okay, opt homebrew bin stockfish. Depth, we have, I've been last time I did it depth 16, so we will do depth 16. Decline, oh sorry, okay fine, it will take depth 20, which is not too bad. Is it doing something or no? Okay, it is only asking questions. When will you do something? Fine, go ahead, go with depth 20. Submit answers. Fine, submitted the answers. Got it? Let me build the script. All right, let's see. Is it in current directory or not? I mean, is it in attempt 02 directory or not? I am a little confused. Well, it is reading the files. It is not saying that I don't find all these puzzle files, and also it must be having them. Do you want to generate puzzle training data? Yes, I want to generate that. Okay. All right. Oh, wait, USR local bin stockfish it at this path. I had told you. Oh, sorry. I gave it the wrong path. Okay, all right. I'm sorry. Uh, okay, I think it has already started running the script and generating the file, but so far no puzzle file has been created. Okay, it is just waiting for the file to get created, but it may take a bit of time to create the file, and particularly it often writes the file towards the end. So let me talk to it. Can you stop your program? I will run it myself. Let's see. Okay, it was saying to reading puzzle database. Okay, yeah, it is taking a bit of time. It will generate these many files. Fine. Okay, let's do this. I will run this program. I will generate the output, and then I will come back and we will observe the output. Thank you. Okay, I am back. So it had generated that program. I ran it. There was one or two slight hiccups, but let's not go into those hiccups. They are not material to the spirit of the enterprise. So we have now these two files, trainingpuzzles.csv and testpuzzles.csv. Let's have a quick look at what these files look like. So we will just see one of them. So yeah, so there is this puzzle, and it is saying that g3 g8 is the only move that we have. There are no other moves. Okay, and actually what it has done is that it has yeah, during the intermediate time there was some change. It has done that rather than assigning plus 1000 or minus 1000 score to the correct move, it has assigned a score of 0 to the correct move and negative 1000 to all the other moves. So that's how it has incorporated. Yeah, this was slight change that I did while I was offline. And let's have a quick look whether it seems to be correct. We will go to Lichess. Wait a minute, I will be bringing the browser here. Yes. So we will go to the analysis board. We have already copied that fen. Yeah, and so the evaluation of the position is 10 pawns, which is correct. White is completely winning here, and the right move, it says, is g3 g8. Indeed, even here it is very clear that the right move is g3 g8, because g3 g8 very soon leads to the checkmate. g3 g8, then the only move black has is to capture the queen, and then here we go, and it is a checkmate. Okay, great. So we have this testpuzzles.csv and we have trainpuzzles.csv, and now what we will do is simple. We will take testpuzzles.csv, and actually let me remove the top line, this one, the header of the CSV. Similarly, I will do the same thing with training puzzles. This is also a small file. I can just open it in Vim rather than doing anything more complicated, and delete it. And now what I will do is I will say cat, my previous file was trainingdata-augmented.csv, trainingdata-augmented.csv, and then trainingpuzzles.csv, and I will say it combined trainingdata.csv. And similarly, I will cat testdata-augmented.csv and testpuzzles.csv, and I will say combined testdata.csv. All right, now let's count the number of lines. It is yeah, so there were 3.6 million and another 400,000, so there is 4 million. And similarly here we have 400,000. There were 360,000 and 40,000 more, so there is 400,000. An additional one line is because of the header. All right, great. So now we have the file. Now what we will do is let's go to the slide. Yeah, so our plan was that we first need to prepare the data. So we have a starter from the previous data set. We have augmented it with the top 5 moves, and then we have added 400k and 40k puzzle positions. So we are good with the data. Now we need to write the code for the new training. So what we will do is we will bring the previous chess engine, the one which we wrote as a part of the first video, which only has eval here. Okay, and we will say please read chessengine.py and understand what it does. Okay, and then we'll carry forward the conversation after it has read. We will ask it to implement policy head as well. There is one thing that I did not put in slides, which is a implementation matter. When yeah, we will soon come back to Claude, but there is something important to tell here, and that is that when I wrote the code using Claude and did the training, it was taking a lot of memory, and my machine did not have sufficient memory. Note that in the first part, when we were dealing only with evals, we had only to store eval, but now we need to store those output moves as well, that 4672 sized arrays. So it was becoming very complex. So it was more time consuming than what I could afford. It was more memory consuming than what I could afford. Then I figured out that there is something known as sparse tensors. So then I implemented sparse tensors, because note that out of 4672 moves which are valid, only five of those probabilities will have non-zero values. Other 4672 minus 5 will have zero values. So we can use the idea of a sparse tensor to greatly compress the way in which the tensors are stored, and that then led me to have an easy time while storing all the tensors at the time of training. Okay, so we will do that. So let's see what it is telling us. Yeah, so it has figured out that purpose is to evaluate board neural network that evaluates board positions. Fine. And maps pawn units. Final output is between -1 and +1. There is this network architecture. There is the Hoover loss with beta equal to 0.2 and some more things. Fine. All right. So what I want to, okay, it is saying something more. Key detail for your puzzle task. The training data format only uses the first two columns, correct? And the remaining columns are ignored. Yeah, so but now I want to change it. I want to enhance this network with a policy head. The training files now, the training files combined training data.csv and combined test data.csv contain the top 5 moves for each position. The scores provided in the training files are the deltas from the base position in the units of centipawns. Note there is slight detail, which is this. I think I have not emphasized it well enough. Yeah, that while the eval is in pawns, this all is, I think, sorry, what did I open? I opened test puzzle, sorry, combined test. Yeah. While the eval is in the unit of set no wrap, yeah, while eval is in the unit of pawns, yeah, so -4.45, -1.22 and so on. You see, they are small values because they are in the unit of pawns, but the deltas are in the units of centipawns. So you will see big values like 775 and -355 and so on. So this is a detail. If we miss that detail, then it will be some circus to correct the bug. Okay, so I have already provided you scores are in the units of centipons. I want to uh, use this to create a policy head. Uh, do I want to provide any further details? Oh yeah, one more thing. For representing the moves, I want to use 64 cross 73 board representations, move representation, where each move is represented by source square comma move type. If you remember, we have discussed this source square comma move type earlier. Where was it? Yeah, each we encode each move as source square comma move type. This is well known to Claude, because actually it was Claude only who suggested to me that engines like AlphaZero use it. So it will definitely be knowing this. So anyway, we will just go ahead and see if what it does. Let's see. What is it trying to do? Git log. I don't know why it wants to do git log. Whatever. Okay, fine. Go ahead. Uh, Git ls3. I'll just say, can you? Okay, fine. There is no need to do git and all. No? Just I have given you the code and asked you to make some changes to the code. Why are you exploring all the git and all? Explore, play and inference code. Maybe it just wants to learn all that it can before taking any decisions. By reading all the files and git and everything, it just wants to learn everything that is possible so that it can make the best possible choice. Not a bad thing, yeah, but I know that you are not going to get anything from git commands. I will pause for now, and when it is done, then I will restart the video. Okay, after some minutes, Claude returned back. It is asking, saying that I have written up a plan and I am ready to execute. Let's just read the plan. This is what we humans are left for. We don't code, we just read the plan. What the heck? All right, let's see. Okay. Something more. Yeah. Here is Claude's plan. It took a good 2 minutes. No, it took more than 2 minutes. Whatever. Okay. Add a policy head to the existing chestnut using AlphaZero style 64 star 73 move encoding. So AlphaZero is what probably introduced this move encoding. The shared residual trunk is unchanged. So residual trunk meaning this what I called backbone of the network. So this backbone is unchanged, and then there will be value add and a policy head. Let's see. A new policy head branches off after the residual tower alongside the existing value head. Yes, so there is this residual tower consisting of 8 resonets, and after that there are the two heads. Training becomes multitask. Yes, so the total loss will be value loss, the summation of the two losses. Files to modify, yes, all changes we will do it in this. I want only one file because I do the training on Databricks notebook, and if there are multiple files, I don't know, I will have to do create multiple notebooks. I don't know how to import and all. It's not a whole lot of code, so we will just write a single file. Move encoding, yeah, so it says 64 source squares and then 73 move types. First 56 move types are queen-like moves. This is what we have discussed during our presentation. Yeah, so first 56 basic moves, the queen-like moves, 8 knight moves, 9 under promotion moves. So that's what it should say probably. Yeah, 8 knight moves and 9 under promotion moves. Then there are some new functions. It is introducing a function from the move to the to our representation, and the other way around. Network architecture is there is a convolutional layer. So after the series of the VESNets, there will be a convolutional layer and batch normalization followed you have to followed by batch normalization. Okay, sorry, so convolutional layer itself outputs a 73 sized vector. Okay, I'm not understanding fully, but what I see is that finally the output is like 73 cross 8 cross 8, which is what we need. Okay. And then there are some other things that it is doing. Let's not worry too much about them. It is saying masked cross entropy, mask non-scored moves with -1 E9. Okay, yeah, so so it is saying that okay, for 5 moves you will provide me the probabilities. For the other moves I will have this -1 E9, which is essentially minus infinity as the move before softmax. So the logits will be minus infinity, so that the probabilities will become then 0. Okay, some more things. Chess evaluator, something fine. Okay, this is I will ask it to execute this plan, and then there are a few things that we want to do but it has not done. One is, let's go through our slides because we had discovered some things. This was done, this was done. Okay. One thing is that, okay, there are 2 things that we will specifically need to do, which this has not done. One is legal move masking, and the other is sparse tensors. Okay, so it will take some time to write the code, and I will be back once it is done. Okay, so it was done with all the coding, and now let's do those 2 things which were remaining. And let's see, let's first ask it, do you think it is a good idea to implement legal move masking so that network can learn about legal versus illegal moves? Okay, maybe it would have been a good idea to read the file just a bit before we did this change. Oh, maybe it's not too late yet. Okay, it says network doesn't need to learn legality, it already knows it implicitly. The policy targets only have one probability mass on the scored move. Okay, adding legal, so okay, it is saying that it is not a good idea. Legal move prediction. What I mean is, we should not be considering the logits of illegal moves. We should force them to minus infinity so that probabilities of illegal moves are 0. That way, network would only learn how to rank legal moves rather than having to learn how to push down the logits of illegal moves. Let's see. So first time around it said that I am not comfortable with the illegal move masking, but we are pushing back. Let's see. Okay, it says, that's already what the current implementation have. Okay, it already has legal move, what I was calling legal move masking. Okay, got it. Great, great. Okay, so now let's have a very quick look at at the current file, chessengine.py. How many lines are there? This is some 1200 lines of code. Okay, and specifically I would be interested in the model chessnet. There is this yeah, it would be good to just go through the model line by line and match it with the architecture that we have seen in the slides. Initially there is a convolutional layer followed by the batch normalization layer. That is, sorry, yeah, so the initially, so this is the initial convolution and a batch normalization layer. All right, then there is another convolution and batch normalization. uh, Actually, yeah, I have put here only one, but why is there another one? There are two of these. Okay, okay, sorry. The second one just changes something. The second one, I think I have missed it here. Let me go to the original thing. There is a 3 cross 3. There, okay, I am unable to figure out. Okay, this is something which I am unable to answer. Maybe it has introduced, we didn't instruct it anything. Maybe it has introduced another convolutional layers before the tower of the residual blocks. But okay, fine, we will just live with this. Okay, so then there is this ResNet, the residual tower consisting of 256 channels. What did we have? Did we have 256 channels, or yeah, so fine, output is 256, so this is 256 channels only. Great. And the number of these, we wanted 8. Yeah, so there is this 8 only. All right, great. Then there is a value head, which is already coded up, which was present earlier also, and value head consists of convolution and then 2 fully connected layers. So yeah, a convolution and then 2 fully connected layers, and it has coded up a policy head. Okay, it is saying policy head is optional. I didn't really want it optional, no problem. It is convolution, and then in the end you give num move. So the output is these logits, whose and the number of these logits is num move types, and num move types is 73. Okay, all right. So they, and internally it is a 8 cross 8 thing going on. So finally there will be 8 cross 8 cross 73 logits. All right, so this is the network architecture. Maybe we should have read it from the forward policy, from the forward function, which is the which tells us which layers come after which layers, and finally there is a 73 cross 8 cross 8 output. All right, great. Now let us see, do you think that implementing sparse uh, tensors for the policy tensors is a good idea to save up on the memory? I am worried that we will not be able to store all 4M plus 400k positions and their evals and top 5 moves in 128 GB memory that I have. Let's see. Okay, it says that the current implementation stores handles this as well. The policy tensors are not stored, they are built on fly. What is stored per position is just a compact list. Okay, all right, fine. Okay, great. So, I don't know what has happened because last time when I did everything, it stored, it didn't do sparse representation, and I was facing memory problem, and then I did it. And similarly, even legal move masking it didn't do, and it was giving bad things, bad moves as output, and then I figured this out. So I'm not, I don't know why it has done all these things by itself. Maybe it is, I don't know. Claude is a very fast evolving product, so I don't know what's happening, but it is just doing things that I wanted it to do by itself. Magical. Okay, great. So now we have this training file. Let me close Claude now and close this tab completely. Yeah. Now what we will do is we will copy. We already have the script. We also have the okay. There is one change that we will do. We will mm, have, there should be a policy weight. Uh, there is no policy, there is no weight. I wanted to have not give the equal weight to both. Okay, but it has okay, yeah, there is policy lambda, weight for policy loss. So it will let's see where it does. Policy lambda is self dot policy lambda. Man, you are just where do you use it? Yeah, so it is computing total loss as value loss plus policy lambda into policy loss. I know from my experience that I would want it to be not 1 but 0.1. So this is what I will do. Policy lambda, I will change it to 0.1. All right. Now what I will do is I will put the training files in S3. I will copy this chessengine.py in a Databricks notebook and I will run everything. Okay, so let's do, I will not show the complete running here, but let me do just the starting things right here just for the fun of it. So just a minute, I will log in. Wait, I need to log into this Databricks account. Just a minute. Where, wait. How, not like this, but like, This is the data, this is the place where I store the data, wake.pandey and engine, and these are some files from the previous run, and I think I have already uploaded. So what was the final thing? Combined something, combined test data.csv and combined training data.csv. I may have already stored this file. Let me see. Combined test data and combined training data.csv. So I already have these files available. Great. So now what I will do is I will go here, and I have to, let me create new something, a new notebook. I will just start this thing here. Yeah, it is starting now. To begin with, I need to install Python chess and I think it's pip install, pip3 install Python chess and pip3 install. I think remaining things have installed only. Maybe one more dependency I need, I am forgetting, we will figure out. And then I will also copy this file. I won't be able to copy here because I am in tmux, so let me go somewhere else. I will copy this complete file and I write everything in one file, because when I'm working with the Databricks notebook, it is easier that way. I have this complete thing here which I will copy here. And even the last time, the way I had made everything was that it does take it does knows where in S3 I have stored. So it knows about the S3 location. Where else? Yeah, you see, it knows about the S3 location. It knows about how that it has to store the final models also in S3. So all these things it already is aware of. So now I will, after this cluster has started, I will do this, and I will run this program and generate the model. Now since generating the model takes like 2 days or something, I will not, and I have already generated a model, so I will not be waiting for 2 days for this one to finish. Rather, I will use the model which I have generated earlier, and then we will do some performance testing on top of that model. Okay, so I had done the training and using the script very similar to what I generated in front of this video. There are So now we will view the we will do some gameplay and see how it performs. But few things I want to point out before we go to the gameplay. One is that I stored the loss trajectory, and I just wanted to give a feel. It's like give a feel of what how it looks like, and that is yeah. So the loss. This is yeah, so this is, yeah, probably this is not the first training. The loss improvement was not so small that it started from 0.41 and ended at like 0.35, but this is just to give a slight feel of how the output looks like, how the loss trajectory looks like. So the first few things are for training data, and the last ones are for validation data. And yeah, and as you can see, policy loss is consistently policy loss is consistently like 10x. Actually, in this case it's like more like 30x of the validation of the value loss, and that is why we had set policy loss weight to be 0.1. Maybe I should have set it even further, like 0.03 or something, and that might have been better. W1 metric is one of the metrics that I use. This I devised for the value, how good is my value head doing, eval head doing. So W1 tells us that in how many cases is my prediction of value within 1 unit of the actual eval. Note that while the model outputs between -1 and +1, we actually take it to -infinity and +infinity by applying reverse tan h, and then there is a little bit more things involved. You can find that in the code. So yeah, so I have been able to finally get to like 54% within one eval. So if what it means is that if actual eval is of a position is, let's say 1.5, means reasonably favorable for white, then my model will output somewhere between 0.5 and 2.5 54.4% of the times in training data, and like 53% of the time in test data. It is only after this training and all was finished I realized that loss is quite the loss values are quite abstract. We don't know what is good, what is bad, and that is why for eval head I had devised this thing, so that I have some sense how good is the network doing. Unfortunately, I didn't do it for the policy function. In the retrospect I should have done it, and I think what I should have done is that since I am going to pick like top 5 or top 6 moves, top moves suggested by the engine, so I should have asked it in what fraction of positions is the actual top move as suggested by Stockfish within is in what cases is the actual top move one of the top 5 moves outputted by you as well. In that case I am assured that the actual top move will be explored by us, and in what fraction of cases it happens. So this is a miss from my side, maybe, but this is not the last iteration. Maybe next I will do that, and then that will give me further ideas of improvement. Actually, I have more ideas of improvement anyway. We are nowhere close to saturating the performance of the engine. Another thing that I want to point out is this. Yeah, let's put it in slideshow only. So there is one practical thing that we should know, that suppose that you create a model M, and then you figure out that you can improve your network without changing the network architecture. So network architecture remains the same. In that case, so some things in which you want to change the training but you don't want to change the network architecture are things like, let's say, loss function. Earlier I was using some loss function, now I want to use some other loss function. Similarly, we put legal move masking. Earlier I didn't have legal move masking, then I had legal move masking. Similarly, we want to augment the data. We are training with some training positions, and then we realize that I want some more training positions. So we are changing the training, but we are not changing the network. In such cases, we shouldn't start training from scratch. Rather, we should take the model, the latest model that we have, and then we can further fine tune it with these changes. So that way we converge faster. We don't need to always train from scratch. So that is another practical matter that I learned during the making of this network and associated chess playing engine. Then there is one more thing that I just want to cursorily say. We will not deep dive into it. What I did, so for playing the game, what I did was that in the last video, at the time of playing the game, I was running the network on my laptop itself. and so I was not using GPU, and so the gameplay was very slow, and to play one game it will take like maybe 5 6 7 hours. So it was very very slow, and I wanted to make it fast, so I made an inference server which I run on the cloud, and that cloud has access to GPU. So I run an inference server. So what I did was that we I what I do now is that I upload my model to Hugging Face. So I have created a repository, let's call it in Git lingo, called chess model 01, and I update my models, whichever checkpoint I get and which are the models that I want to play with. I update these models here, and then I have a chess server which is aware of the model itself. So yeah, so it has all the network architecture code copied from the training script only, and what else? Yeah, yeah, so it knows the model. It downloads the weights from Hugging Face. So this is this is I think the last model that I had created. It downloads it from Hugging Face, and then it starts a server, and I get a reverse proxy system from Cloudflare. So I am you see I am installing something from Cloudflare, and then my model is available. So okay, yeah, and I use what did I use? I think I used Flask. Yeah, I used Flask to as the backend, which exposes a data point called evaluate with policy. So anybody can call this data point evaluate with policy. My engine will call it, and it will give a bunch of fence as in the positions, and then for each position this backend will invoke the model. Actually, it will create one big tensor out of the board representation of all these fences, or all these fence. So it will create one big tensor, and then call the model and evaluate all these positions which are converted to tensors in one go. So we will get the scores as well as the top moves, and it will then provide the top moves in the response. So this is the response data. So so this is the way I play chess now. I run engine now, and yeah, and the server will be live at some location. Okay, so then on the client side, I have created a file called play match multi-process with policy. So it what it does is that it starts a number of workers. So we will play many games in parallel, and it says that I will play maybe 10 games, or maybe by default 100 games with stockfish, with various levels of stockfish, starting from start skill to end skills. So I will play with stockfish level 0, with the stockfish level 1. With each level I will play these many games, and this is the depth to which this is the depth to which I will search. I as in we will, during the gameplay we search till some depth. So maybe we will do default 2 is very low. We will definitely do like 5 ply, 6 ply, up till 8 ply search. That is reasonable, and then there are some more parameters. Let's not go, yeah, but very important is top K. So at each level of depth I will explore top K best moves. So more is the top K, more time consuming it becomes, and also more thorough it becomes. If you say top K equal to infinity, then you are essentially not using your policy decisions at all. So we typically take 5 or 6 top K moves. There are some more things actually. Let's go through them. Probability threshold means that let's say that top we are having top K equal to 6, but first 4 moves itself account for more than 0.95% of total probability, huh? So first move maybe itself is like 80% probable to be best move, second move is 10% probable to be best move, third move is like 4% probable to be best move, and fourth move is like 2% probable to be next move, so first four moves itself are the best move is with 96% probability one of the top four moves. And in that case, if probability threshold is set as 95%, then we just cover four moves. We just explore these four moves, not like full six moves as dictated by top K. So this is to go deeper in to save time. We don't want to explore the moves which are very less likely to be the best moves. And the min move says that even if, so min move is sort of an override for probability threshold, that even if one move is like 97% likely to be the best move, we want to explore at least let's say two moves, or at least three moves definitely. So whatever default is one, but whatever we want to provide, we can provide. Server URL is the URL of this Cloudflare URL. Time is the time we give to Stockfish for per move, and this is the path of Stockfish. This is the output where the results are written. Model path is now not needed at all. We don't do anything with model path. Yeah, whatever. Yeah, nothing. Yeah, this is a legacy thing. Maybe we should remove it, because we now query the inference server and we don't have anything to do with model path. So we have some, so this is one script which runs everything, and I have already updated the URL to correct one. Every time I run the notebook, I get a different URL. So yen prospects influences something, and this is yen prospects influences something. All right. So yeah, it's not that we will complete the whole game, but just to give a feel, we will just watch. So here top K is 10. Top K is 10. Let me just do things slightly nicer. I want to play 10 games. I want to have 4 workers. Start skill, let me give start skill as 0. And depth, I want to go to depth 5. Fine, depth 5 is good. Top K is 10 is good enough. And probability threshold 0.95, something, whatever. Yeah. It's just to give the feel of how the gameplay looks like. Yeah, so here you see Stockfish has we are playing 10 games. We are right now playing 4 games. In game 1 and 3 it is neural network which is white. In games 2 and 4 it is Stockfish which is white, and they are playing their games. And if you see the server logs will periodically tell us that yeah, it is getting requests and it is returning with responses. So this is the way the game keeps on happening, and once the game has is done, then we will get to know the result. The game is happening. I can let it happen, but I anyway will show you the result. It's happening quite fast. It's like 8 moves are already done. Maybe we should just enjoy the game for a while. Once one game is done, then we can also look at that game. Note that right now we are playing with a Stockfish level 0, which is very weak. It doesn't do any blunders. It's just quite weak, and so it is easy to defeat it. So maybe we will defeat it very quickly. You see, in game 1 the eval is already +3. So meaning our engine is winning very much. So in game, so maybe the game, one of the games will finish quite soon. Let's give it some time and have one game finish, and then we will see the game. Meanwhile, where to go? Yeah, sorry. Yeah, let me. I will copy from here. I need to copy from here. So let me close this. Actually, close this also. Close this also. Just and attempt 02. Yeah. So we will see. Yeah. All right. Game two. Black is winning. Yeah. So these are going to be easy wins mm, for my engine, because this is stockfish level 0. We are already in some mating positions now. Uh, let's have let's hope that in with okay, fine, one game is finished, game 3 is finished, and neural network has won. Let's see the game 3. uh, yeah, this is game 3. We will just have a quick look at this game. We have copied that fen. So pgn is some portable game notation of something. We have copied it, and white stockfish was white. So let's just see from the beginning how this game looks like. d4. Yeah, we will quickly see. Yeah, this is the queen pawn opening. Fine, all right. This is queen's gambit. Okay, there is no silly move so far from anyone. This is a slightly unusual move. I don't think people played it that well. I don't think this is a very strong move. Well, I don't know chess very well. Okay, all right. People keep playing. This number shows the strong stockfish evaluation. So this we can take as the ground truth. Queens have been exchanged already. Okay, at this point, Mr. Stockfish level 0 did some mistake, and that is why the eval has gone from 0.9 to 3.1. And let's see. Okay, yeah, it's not even trying to save this. Okay, yeah, the mistake was that now this knight is trapped. Well, no, knight can go here, but then I can take with my queen. I can take with my bishop. I don't know why this position is so bad for black, but it apparently is, and we take the knight. Okay, anyway, the game continues and continues. Maybe let's look at one more blunder or bad move which is done by black. It takes the pawn. Apparently it's not that bad, but and this rook was lost anyway. But yeah, but this is apparently a bad move. And okay, and the game continues, and finally we are able to. Let's see towards the end. We are. Can we give a checkmate? Yes, it gives a check. The king goes right. It gives a check. King goes right again, and finally it does discover mate in one. So the final mate in one position. Mate in one move was one of the top 5 moves, so this is quite good. Now let's also so that we can see that we are, it's not that we are very good engine. If we say that start skill is like, let's say 16, and end skill is 16, so now we'll play against very strong stockfish level, and there is no way we can win against this level. So let's just see if it actually happens. So we are playing against stockfish level 16. I know that stockfish level 5 or 6, skill level 5 or 6 is our max. So let's yeah, this game may last a little bit more because our engine is also not that weak, and stockfish is also level 16. So I will pause the video and come back once one of the game is finished. Okay, so one game with stockfish level 16 just finished, and we will now quickly review that game. Stockfish level 16, actually multiple games have finished. Yeah. And You see, in the first game, neural net is white and it is black, which has won. In the second game, stockfish is white and stockfish has won. In third game, stockfish is black and again black has won. So stockfish level 16, we very well know it is out of our reach. Uh, but good too. Just let's just have a quick look at a game. Is it that we do some blunder, or is it something else, or is it like a gradual decline? uh, okay, who is black and who is white in this game? uh, neural net is white and stockfish is black. Okay, let's see. It's the same set of moves, if you remember, as what we found against playing with stockfish 0. Queen's gambit accepted it is. So far, okay, so we challenged this pawn and this just moved its pawn forward, and we are now on sort of defensive, and now it has taken that pawn. Okay, fine, this is like a silly move, silly mistake only. Now we should have not, this a4 was a bad move. Okay, now we have a pawn down, but hey, we can take back, we could have taken back this pawn. This is what in this engine is saying, but we didn't do that. We went somewhere else, and now okay, we have taken this pawn. Okay, fine. Okay, castling. So far it's silent. Suddenly we neural network says that I will take out queen and maybe threaten mate in one or something, but castling is very cool. Okay, for this is like I don't know what the eval also doesn't change too much from -1.2 to -1.6, but it just sacrifices its knight for nothing really, for just a pawn. Okay, for two pawns, not for one pawn, but for two pawns. And now it has pinned this apparent, it looks to me that it was something good. It has pinned this rook, and now it should take it maybe. Okay, it doesn't. If I were there, I would have taken this rook, but apparently neither did my engine think it is good, taking the rook is good, nor does the standard stockfish, Leach's stockfish says taking is good. Whatever, fine. Maybe at some later point we will take. Okay, fine, good. So finally we have taken the rook and also exchanged the queens. At this point, if I compare the material, it is two rooks and two minor pieces versus a rook and four minor pieces. So clearly black is has gotten much better. Okay, and I don't, yeah, if I spend a lot of time, then maybe I will be able to understand why one particular move is good or one particular move is bad. But the game carries on for quite some time, and we keep losing. We keep the evaluation keeps going down. And finally we are just surrounded by black pieces. Even our rook is gone, and after some time, okay, now stock, it is minus. Okay, note that even stockfish level 16 is we are playing against stockfish level 16, but it is not able to catch this mate in 7. No, it is able to catch. It is able to catch. Yeah, fine. It is level 16, so it does a mistake at 16 deep, so it is able to catch mate in 7. 2, 3, 2, 1, and then finally, I'm sure it will mate. Okay, finally there is this checkmate. Okay, so we saw that against level 0, we we defeated level 0 very very nicely, but we lost against level 16, which is accepted, which is expected. And finally, what we will do is just look at the performance of our engine, summary of the performance of our engine. So last time when we were doing value head only, we could do only 3 ply search, and you see we were able to defeat level 0. We won 7 games out of 10. Level 1 we were roughly equal with level 1. Level 2 also we won more than we lost. There is some variability also, there is some randomness also. So our performance on level 2 was better than our performance on level 1. That is not can't be true. It is just a statistical anomaly. So we can say that we were somewhere between level 1 and 2, maybe at most level 2, definitely not a level 3. Level 3 just defeated us. Skill level 3 defeated us hands down. Okay, so somewhere at the most we were at the same rating as level 2, maybe slightly lesser than level 2. And then now when we do value head as well as policy head, I did an 8-ply search and top K of 6. Then you see till level 4 we are very comfortably winning. Level 5 also we win 4 matches and we win 4 games and we lose 3 games. So probably we are better than level 5. Level 6 is where we start losing. We win 4 and we lose 5. So at the most we are as strong as Stockfish level 6. So earlier we were as strong as Stockfish level 2 or 3. Now we are as strong as Stockfish level 6 at most. And Stockfish levels go up to like 20. So we have a long way to cover. So it's level 2 3 versus level 6. What does that mean? We covered that earlier in this video. So level, let me see if I can open this image in new tab. Yeah, so level 2 means a rating of 1566 roughly. So we were slightly less than level 2. We were between level 1 and 2. And so I had said that maybe our rating is like 1400. Last time I said that. Yeah, maybe it was more like 1500. But now we are close to level 6. So just a minute, I will be back. So with a rating of around 2300, this gets a little bit more serious. So 2300 for a human is quite a strong level. So chess titles, if you search for chess titles, it is at a candidate master level. So so you see the top level is a Grandmaster, for which you need a rating minimum 2500, and for International Master you need a rating of at least 2400. There are some other norm requirements, let's not go into them. And then for FIDE Master you need 2300 or more, and similarly for Candidate Master actually you need 2200 or more. So we are at the level of like FIDE Master, something like 2300. And in the whole world there are something like 14,000 or 9 and 4, 13, 14, 15. So maybe 16,000 players are there which are at a level of FIDE Master or more, and our chess engine looks like is operating at a level of FIDE Master. So this is quite encouraging. So that is where we have reached in with another few weeks worth of work in our chess engine. Finally, there are so we have reached 2300 level. There is a long way to go. As I said, the grandmasters are like at 2500, best human is at like 2900, and best engines are at like 3500. So we will see till what point we are able to push without demanding too much compute resources or too much time in it. And so firstly, we were doing, to summarize, we were doing 3-ply search in the first video, and now we are able to do 8-ply search. But there is one thing, that now we are doing constant 8-ply search. We regard all moves as equally good everywhere we go 8-ply. But not all branches are equally promising. In some branches maybe we can get away with the lower depth and we can exchange it for a deeper investigation in some branches. And I have heard that this is the idea behind MCTS, Monte Carlo tree search. So maybe we will explore this in some coming weeks or months. There is another thing, that so far there is no reinforcement learning. So the whole goal was to understand reinforcement learning, but so far we have been making progress using Stockfish as our guru. Stockfish is teaching us and we are learning it. So at some point we will need to have the network learn from playing games rather than being given evals and policies. So that is something. So we have to reach a stage. So at some point we will reach a stage where we don't tell the engine or our learning system that this position is good, this position is bad, these are the top 5 best moves in this position. We should be reaching a situation where we just have it play the game, maybe play it against itself, self-play, or maybe play against some strong Stockfish or some other engine, and then have a look at the result and analyze the result, figure out where you did the mistake and learn from it. So that will be the reinforcement learning. We will at some point reach there. But even within eval and policy area, there is scope of doing more things. One possibility is that right now we are not telling the engine which moves are legal and which moves are not. We are not telling the network which moves are legal and which moves are illegal. Using legal move masking, we are helping it out that we compute loss only from the logits for the legal moves, and we don't consider illegal moves in computing the logits. So that way we are helping it slightly, but it doesn't explicitly know which moves are legal and which moves are not. So providing legal moves in the input itself, maybe it will help the engine, help the network. Similarly, maybe we can have mixture of experts type of setting, because we know that as a human, we know that end games feel very differently from middle games. Middle games feel very differently from openings. And different types of end games feel very different. Pawn end games are very, very different from, let's say, rook end games. So can we have a mixture of expert type of model where one expert will naturally specialize in one type of game? So that is something I can try. We know that mixture of expert does help in LLMs. So maybe it will help us in chess engine as well. And another thing is that maybe not all experts in a mixture of expert setting need be equally complex. So maybe we can have, so we currently have 8 ResNet of depth 8. So maybe we can have ResNet of depth 4, and then we have a routing layer, the mixture of expert routing layer, and then some networks are just too deep, too further deep, or maybe 0 further deep. They directly have some fully connected layer. And some networks are really deep. They have like 10 of 12 deep ResNets after the initial 4 ResNets. So some are really deep. And that way, maybe simpler positions will be routed to the simpler networks, and they will just quickly say if it's a mate in one, why do you don't need to look a lot, you just say this is the move, this is the right move, and maybe some simpler network, shallow network will help, will operate in those sort of positions. So maybe, yeah, that is one idea. Maybe I will try it out. Having valid moves, mixture of expert. There are more ideas. Right now we have used, so one idea that has been in my mind is that right now we are using standard 3x3 convolutional kernels. But is it that maybe for the game of chess we should have a diagonal, a horizontal convolution layer, convolution. So it is not like a 3x3 convolution layers come from the image processing and all, but this is chess. So maybe there is a vertical move kernel. So it is like 8x1 kernel, or similarly 1x8 kernel, similarly diagonal kernels. So maybe those convolution layers are more suitable for chess, apart from, so maybe we can have, so we have like 384 256 channels for these 3x3 convolutions. So maybe some channels can be for these specific chess specific convolutions, and some for normal convolutions, normal 3x3 convolutions. So this is one idea. So maybe there can be more ideas just to improve eval and policy. So we will see. This is the end of the video. I am having fun making these chess engines. I have devoted, like, maybe in last 1 month I would have devoted maybe like 12 to 15 days in this enterprise. So let us see where it leads, how strong we can get, and how much we can learn from building an amazing chess engine. Thank you everyone who is watching. As always, feel free to comment on the video, feel free to give me any suggestions that you may have about what we can try, and particularly if you have already implemented chess engine and you would like to just try out some things that you are not able to try, let me know. Thank you very much. Have a good day and have a good year next, good 2026. Thank you and bye.